So let's draw some pictures. We are going to draw pictures for every permutation of the geometries that result from a steric number of 2 through a steric number of 6. You do not have to go beyond that. So we're sticking with 2 through 6. And these are going to be my best pictures drawn on flat paper. We'll have some work with models, and I will also have links to some other YouTube videos that are really helpful. So steric number of 2, my basic geometry, my electron geometry is linear. And what that means is that if A is my central atom and B are the two things that are attached to it, I've got them attached with single bonds. It doesn't have to be a single bond. This is just kind of a generic picture. Then the farthest apart the B's can get in 3D space is 180 degrees apart. So what I have labeled here in orange, my bond angle is 180 degrees, and the B atoms are as far apart as they can get in 3D space. And that's it. That's it for steric number 2. When you look at this where this actually represents the shape, they're in a straight line, you would call this linear. Okay, steric number 3. The electron geometry is called trigonal planar. So 3 things as far apart as they can get in 3D space. So it's like having A as the central atom, and now I have 3 B's connected to it. When they get as far apart as possible, the result is that they are 120 degrees apart, and just due to the nature of there being 3 of them, they're all in the same plane. So that's why the planar part is there. And you could draw a triangle around it, right? There's 3 things, that's why it's called trigonal, and then they're in the same plane, so it's called planar. So A in the middle, 3 B's bonded to the A. Again, I've drawn single bonds. It doesn't have to be a single bond. And the bond angle is 120 degrees. So the angle between BA and another B is 120 degrees. And if this were my shape, right, with 3 atoms connected, I would call this trigonal planar. The electron geometry and the name of the shape would be the same. Now, I can have a steric number of 3, but only a coordination number of 2. So if I have A connected to 2B atoms separately, and A has a lone pair, that's 3 things around A, but only 2 of them are atoms. My electron geometry is still trigonal planar. So my first approximation is that they're all 120 degrees apart. However, if I'm thinking about what the bond angles would really be, this is where the repulsion order rule comes in. A lone pair being repelled by a bonding pair is a stronger repulsion than the bonding pair and the bonding pair. The result is that it pushes down on this bond angle and kind of squishes it a little bit. So this bond angle would be less than 120 degrees. The degree to which it is less than 120 depends on the specific molecule. Now, if I want to name this shape, I'm ignoring the electrons and just looking at the A's and the B's. The name of this shape is bent. It looks like you took the linear one and bent it when we put the lone pair in. So that is the very, meaningful name of this shape. Okay, let's do steric number 4, which is tetrahedral. So 4 things as far apart as they can get in 3D space means they are 109.5 degrees apart. So I have A in the middle. If I draw a bond to a B straight up, and then I draw a bond to a B in the same plane, I'm going 109.5 degrees before I draw that bond. Now, for the other 2 B's that are connected, they cannot be connected in the same plane and still be 109.5 degrees apart. So now we have to introduce these perspective bonds. So if you see a wedge, which is like this shaded in arrow where it's like skinny toward the center atom and then wide toward the outer atom, that means it's coming out at you. So B would be coming out at you, and it's still 109.5 degrees away from every other B in here. And then going back, so going behind the board, behind the screen, behind the paper, we use dashes to do this. So for tetrahedral, I have 2 in the plane, 1 coming out, 1 going back. Now you will see this written in a bunch of different ways. I can write in a bunch of different ways for you so that you get to see what this shape feels like. Now I do want to point out that this A to B dash, those dashes are parallel to each other. They're not in a row. So the dashes in a row mean something different. So make sure you're writing these dashes parallel to each other. Okay, steric number 4. This is a coordination number 4. It's tetrahedral. Steric number 4 with a coordination number of 3. So I've gotten rid of a B and replaced it with a lone pair. Again, my base geometry is still tetrahedral, but now naming this shape with just the B's attached, we end up calling it trigonal pyramidal. And so let me put in the bond angles and whatnot and see if you can see the trigonal pyramidal shape. So I still have 4 things as far apart as they can get. But again, like we saw in the bent structure, if one of those things is a lone pair, it's going to kind of squish these other angles down a little bit. So they'll be less than 1095. For example, in something like ammonia, which remember the Lewis structure that we drew for ammonia, 3 single bonds and a lone pair. Again, they don't have to be single bonds, it just happened to be that in ammonia. That bond angle is 107 degrees. So it's pretty close to 109.5, but it's definitely smaller. So we call this trigonal pyramidal, right? It looks like a little pyramid with 3 sides if you were to like sketch a shape over it. I also want to point out that when I have drawn this, and same for when we did the bent example, the lone pairs sit on the central atom. Do not draw a bond to the lone pair. You might see examples of this in other places. Please don't do it. It looks like you now have 4 electrons here. Now, if you want to do it as your first approximation because it helps you hold the place, that is fine. Just don't forget to take it out and put the lone pair directly on the atom. For steric number 4, we can also go down to a coordination number of 2. So steric number 4, coordination number of 2, I have 2 things that are still connected and 2 spots that are filled with lone pairs. So 2 bonds, 2 lone pairs, but still those 4 things are getting as far apart from each other in 3D space as they can. So our base structure is still tetrahedral, but now I've got 2 lone pairs. My angles are going to get squished even more, and hopefully you've recognized that this might look kind of like water. So water would have this type of shape. The angle in water is 102 degrees, so squished even more than we saw for the ammonia. Now, this also seems like it's drawn in a weird way, right? Like we don't normally draw water with this weird perspective. So I've got a little like rotate this arrow, right? We normally draw water just kind of flat on the page. When you do this now, if you're showing a VSEPR geometry, right, you make sure that that bond angle is around 102 to 109.5. I'm fine with you approximating based on the electron geometry. And then because we just put the lone pairs on the atom, you don't have an indicator to tell you that one lone pair is coming out of the paper and the other one is going back, but that is what you would have, right? If there are four things around oxygen to be as far apart in 3D space as they want to get, they cannot be in the same plane as those two hydrogens and water. And when we name this shape, we very creatively, again, call it bent. Okay, steric number 5, trigonal bipyramidal. This is where we have that addition of applying Bent's rule. So let's put it on the picture. So 5 things as far apart as they can get in 3D space. The result is that you have, if you have A as your central atom, and with the orientation that I've drawn it, we could rotate this thing around in space, but we got to start somewhere, right? I've got going straight up and straight down with an S. That S means small. Those are going to be my axial positions. Now, those two things, right, they're 180 degrees apart, but I've also got some stuff in the middle, so that 180 is not my bond angle. Around the equator, you might like to think of it as, in my equatorial positions, I have the large atoms, and I have 3 of them. So I'm doing 5 things around. When they get as far apart as they can get in 3D space, what they kind of settle into is this sort of axis, right? Axial positions with kind of an equator, which we call equatorial. So the bond angles, the equatorial things are 90 degrees away from the axial things, and the equatorial things are 120 degrees away from each other. So it looks like you took trigonal planar, so just the A and the L's, that looks like trigonal planar, and then we put a little axis on it, which are my axial positions that hold the small atoms. So you can see, right, something in an axial position is 90 degrees away from 3 things. That's considered a smaller space in the area around the central atom than the equatorial positions, where you have 120 degrees around you. All right, so when all 5 things are on here, we call it trigonal bipyramidal. Not as exciting as when we start to put in lone pairs. So steric number of 5, coordination number of 4. My lone pair is considered a large thing. So that lone pair goes into an equatorial position. So what I'm left with are atoms in 2 of the equatorial positions and in the axial positions. Now, with this one lone pair on here, right, it's going to kind of squish my bond angles. So I still have these drawn like a little bit closer to perfect, but the equatorial bond angle is going to be less than 120, and those axial bond angles are going to be less than 90. Now, the way that this shape is named, we call it seesaw, which isn't that easy to see from the positioning that it's in. So I do have a rotated picture. If you were to flip this down on its side, it looks like a seesaw, like you might see at the park, right? Those 2 B's in the equatorial positions, like that's the fulcrum in the middle, and then the axial B's are like right where you would sit in order to rock back and forth on the seesaw. All right, so steric number 5, coordination number 3. So I've replaced 2 spots with lone pairs. Now, the equatorial positions are still the biggest space, so both of my lone pairs go in equatorial positions. What I'm left with are B's in the axial positions, 1 in the equatorial position, and this is named T-shaped, which is kind of hard to see with the way that this has been put in here. So I've also rotated this around so that you can see that if you flip it onto its side also, it looks like the letter T. Now again, it won't be perfect because those bond angles are going to get squished. Those axial bond angles will get squished just a little bit, but it's pretty close to a letter T. Steric number 5, coordination number 2 is linear, which it seems like, I don't know, it seems weird to go back to linear, but 3 lone pairs, slap them in the equatorial positions, and the only thing you're left with are the axial B's. So I have what would be a linear molecule if I'm only counting the atoms. All right, last one, steric number 6, octahedral. It has 6 things connected to the central atom. The farthest apart they can get in 3D space is everything 90 degrees apart. So one way to draw this is A in the middle, a B up, straight up and down, and then right in the, around what looks like the middle, but it isn't necessarily the middle, I've got 2 B's coming out and 2 B's going back. But that's going to form like a square in the middle. So those are all 90 degrees apart. The B on top is 90 degrees from all of the ones in the middle. The B on the bottom, 90 degrees away. There are no axial or equatorial positions in octahedral. They're all equivalent. Every position is equivalent, just like it was in tetrahedral. So any position is 90 degrees away from any other position. So we do not use those words. That's why there was no Bent's rule that applied to steric number 6. And we're going to make some considerations to where we put lone pairs, but electron geometry of octahedral is every position is identical. Now, you might be wondering, and I wondered for a very long time, why this was called octahedral when there are 6 things attached. If you connect the atoms to make just the outline of the 3D shape, you get an 8-sided shape. So you will get an 8-sided shape if you connect all of these pieces with the 6 things around the central atom. All right, steric number of 6, coordination number of 5. So I've got 1 lone pair on here. This is called square pyramidal. So it looks like a pyramid with a square bottom. Now I've chosen to put my lone pair on the very bottom, but all of these positions are equivalent, so it doesn't matter where you put this first lone pair. Steric number of 6, coordination number of 4. So it doesn't matter where you put the first lone pair. However, when you put the second lone pair on, because they're both big things, you want them to be as far apart as possible. So because I have put my first lone pair on the bottom, I'm going to put my second lone pair on the top, as far apart from that other lone pair as I can get. What this leaves me with in terms of just the atoms is a square with everything in the same plane. So this is square planar. Steric number of 6, coordination number of 3. So my first 2 lone pairs, right, when I put one in, it doesn't matter where, put the second one in as far away from that as I can get. When you go to put the third one in, it doesn't matter where it goes. So put the third one in, and what you are left with is T-shaped. And then steric number of 6, coordination number of 2, 4 lone pairs leaves you with a linear molecule.